Are you sure you are living in an absolute reality? What if the universe we see and live is a product of mere choices of us? What is the guarantee that we are truly alive? In the case of death, is that a real thing to be concerned about? What if we die and step into a new life? Hearing the idea that we might step into another world after death may sound a bit philosophical. But there is a secret that universe has hidden within it. A hopeless cat, swinging between life and death. What if the state of a radioactive particle determines the cat's life? Welcome to Sahapadi, the classmate. In this video, we are going to talk about Schrödinger's cat, one of the simplest explanations of the quantum theory, the scientific revolution of the 20th century. Schrödinger's cat is a thought experiment, meaning an experiment that can only be performed through thought. This is because there are some practical difficulties in performing it in reality. The scientist Erwin Schrödinger proposed this experiment in 1935. A cat is placed inside a moderately large steel box. In another corner of the same box, placed a radioactive substance. Radioactivity is a property where a nucleus of an atom is unstable and emits radiations. Generally, heavy atoms tend to exhibit radioactivity. I have placed a special type of radioactive material in one part of the box. The peculiarity of this radioactive substance is that the probability of one atom decaying or not decaying in 1 hour is 50-50. Which means the probability is equal, just like getting head or tail when we toss a coin. Next to this radioactive substance, I have placed a Geiger counter. A Geiger counter is a device that detects radioactivity. Connected to this Geiger counter, I have placed a hammer and a vial of poison. If an atom in the radioactive substance ever decays, the radiation from that decay will fall on the Geiger counter. The Geiger counter will activate the hammer. The hammer will move and smash the poison bottle and the poison gets released. Once the poison is released, the cat nearby will inhale the poisonous gas and die. Let me close the box and wait for 1 hour. Erwin Schrödinger asks us a question regarding that 1 hour of waiting. Is that cat alive or is it dead? Here, the cat's life is decided by that single radioactive particle. The cat is saved only if that substance does not decay. If it decays, the cat must be dead. We first mentioned that the radioactive substance has a 50% of chance of decaying or not decaying. Until we open the box and see the cat directly, the cat is both alive and dead in our minds at the same time. Can an object simultaneously assume two different states? Through this experiment, Erwin Schrödinger intended to point out a fundamental problem with the quantum theory. Before talking about what that problem is, we need to know a few other things. One of them is the difference between classical mechanics and quantum mechanics. Classical mechanics or Newtonian mechanics is a completely deterministic branch of science. Classical mechanics offers us precise calculations regarding various properties of objects. For example, the position of an object, its velocity, momentum, acceleration, energy, and so on. Now, the characteristics of quantum mechanics or mechanical theories concerning particles is that they are probabilistic. That is, we can only ever provide probable values in quantum mechanics. It was Louis de Broglie who first stated that all objects around us exhibit two natures. One is particle nature. All objects around us are made up of particles. The second is that all these objects also exhibit a wave nature. In fact, as we go to smaller and smaller scales, the wave nature becomes more prominent. In 1927, Davison and Germer conducted an experiment. Electrons were continuously fired into a crystal called nickel chloride. Their aim was to observe the pattern of the electrons bouncing back after hitting the nickel chloride. Electrons are particles, so that the spot where the electrons hit would get a precise point. However, when this experiment was finished, they accidentally got a different result. They got a pattern like when the same experiment was done using X-rays. We know that X-rays are electromagnetic waves. Through this experiment, they confirmed that the electron, as we saw as particles, behave the same way as an electromagnetic radiation. Today's quantum mechanics has been built from various theories of countless scientists like Louis de Broglie, Erwin Schrödinger, Werner Heisenberg, Max Born, Max Planck, Albert Einstein, Paul Dirac, and so on. Although everyone contributed to this theory, they had minor differences of opinion among themselves. Max Born was the scientist who first implemented the term probability into quantum mechanics. If particles show wave nature, it will be difficult to measure many of their ordinary quantities. Instead, Max Born says that we can only measure the probability values of these physical quantities. The wave nature of these particles can only be shown as the probability wave. Here, I am turning an electron when we see as a particle into a probability wave. When it was previously considered a particle, we could think of an electron as a particle that always can be found at a precise point. But when we turn it into a probability wave, the possibility of finding the electron is very high only in the peak of this probability wave. However, as we move to other sides of this wave, the possibility of spotting the electron becomes very low. But understand that the possibility is not zero. We can spot the electron sometime, but the highest probability of the electron being found is at the center. Max Born said that all particles can be represented as a probability wave like this. If the electron is a wave, we change it into a mathematical model called wave function. The probability or possibility of this wave function, which was spread widely, shrinks to a single value at the time of measurement. It is based on this theory that Niels Bohr, Werner Heisenberg give an explanation for our quantum mechanics. This framework is called the Copenhagen interpretation of quantum mechanics. Superposition means a state that shows more than one state simultaneously. It is said that all quantities associated with a quantum object, position, energy, momentum, spin, any quantum property is actually always in a superposition state. But this superposition breaks only at that one time. The situation arises where all these states in superposition merge into a single value. When a person from outside or an observer looks at or measures the system, the state of superposition ceases to exist and merges into a single value. This is where the importance of a phenomenon called observer effect comes in. That is, I am trying to observe from outside a quantum system that is running very smoothly, or I am trying to take a measurement. In the instant of that measurement takes place, all the possibilities of that quantum system will shrink to one value, which is what we get. That is, we have lost all other quantum information. Erwin Schrödinger was not at all fond of this quantum superposition mentioned in the Copenhagen interpretation. Schrödinger's cat experiment was actually put forward by Schrödinger is to criticize the Copenhagen interpretation. The decay or not decay of the radioactive atom placed inside the box is what decides the life and death of this cat. That is, according to quantum superposition, what we see inside the box is an atom that is simultaneously decaying and not decaying. The question is, if you talk about superposition for microscopic atoms, why don't you talk about superposition of a large macroscopic objects like a cat? If your atom is in superposition, then my cat is in also superposition state. Along with this, he added one more thing. There is a property called the wave function associated with the quantum objects. That is, the wave function is a mathematical function capable of explaining all the characteristics of quantum object. Schrödinger said that the wave function of an object has no connection with the reality of an object. Therefore, the various possibilities caused by the wave function cannot be simultaneously attributed to an object. When Schrödinger presented this paper, Albert Einstein also came forward to support it. Albert Einstein once ridiculed the use of probability in quantum mechanics by saying, "God does not play dice." The truth is that even as we discuss whether the Copenhagen interpretation is correct or what Erwin Schrödinger and Albert Einstein said is correct, we have not been able to reach a precise answer even today. However, based on the evidences we have received so far, the most effective interpretation of quantum mechanics we accept today is the Copenhagen interpretation. So, one may ask if the Schrödinger's cat experiment is wrong. In fact, we must say it is not wrong. This is because Schrödinger's cat experiment tells us a few other things. If we make a specific change at the microscopic or quantum scales, it is difficult to bring that change to a macroscopic effect. That is, there will always be a boundary to quantum state and macroscopic scale. You have to understand that quantum mechanics has a limitation in explaining the states of large objects. Schrödinger's cat experiment talk about this limitation. Another thing it tells us is that reality is never based on our observation. Reality is not something that only comes into existence when we perform an observation on a system. Reality is already there and we are later observing that reality. The experiment says that there is no cat inside the box that is simultaneously dead and alive. The cat is either alive or the cat is dead. Anyway, the only way for us to know is to open the box and see. By setting aside the state of superposition, we can later observe, assuming that a reality has already existed there. The truth is that even after a long time after proposing this thought experiment, Schrödinger was not ready to accept this quantum superposition. He said, "I do not like it and I am sorry I ever had anything to do with it." What if we approach the experiment in a different way? I slowly opened the box. The cat is dead. But what if in another parallel universe, another me opens another box just like this and sees a cat that is alive inside? Here, the reality is split into two, a situation where both possibilities simultaneously become reality. Does this experiment suggest that the possibility of parallel universes? We can hold it for another time. Thanks for watching and make sure to subscribe.